Hello, Pocatello, room 16, are you there? I know they're there, but can you hear me? Maybe they can hear me and they can't talk back. Yeah, this is really weird. We have, talk about distance learning, we've got another room across the hall. So, not only do we have to go from Idaho Falls to here, so everybody sees our face, I'm gonna have to go next door as well to try to teach part of it. So. But that shows we're growing, which is good. I think we'll have to end up doing 2 sections of these if we continue at this pace. So, do I have room 16 yet?
We're working on it.
Okay. All right, I'll wait for you because it's kind of important. Do that or they can come and sit on the floor here. Hey, Todd, are you up in Idaho Falls? I guess that's enough. Modern technology. Gotta blame the electrical engineer on this one.
We're good.
Okay, room 16, are you there? Hello, room 16.
Yep, we're here.
Hey, good. Sign of life. You know, I can always just walk next door and see it, but it's nice to have you on the remote. And Idaho Falls, you're there. Can everybody, is everybody seeing the PowerPoint or whatever it is, Open Office, nuclear engineering module on your screens?
We can see it in Idaho Falls.
Okay.
We're good next door.
Hey, cool. Okay. And to the operator, I switch back and forth between Moodle and this, but I'll be using the computer for a little while, so. Not Moodle, but Elmo. So anyway, I guess we can start. So we introduced ourselves last time. I'm taking the first lecture, and then I'm going to turn it over probably to Dr. Dunzik-Gugar. I'm not sure where she is right now. She might even be on her way down here. But anyway, I gave you my introduction before. I gave you a little assignment. Just pass them, or, you know, I'm not going to collect them right now, but, and the same with room 16. I'll pick them up after class. And Idaho Falls, if Todd shows up there, get them to him. Okay? So this is a rough outline of what I covered in the past. Now, Dr. Dunzik-Gugar, I think is going to cover essentially the same topics, the same subjects, because these are the most important, I believe, to introducing you to nuclear engineering. So we've already talked about what do you think about nuclear power. You've spent a grand total of 10 minutes writing it down. You know, so it's deep, deep thought, which is great. But it's off the top of your head, which is really great. So you'd be surprised, maybe you wouldn't be surprised, but at some of the answers I get. So it's kind of interesting to me. Because this is Introduction to Engineering, I'm going to take a slightly different tactic, I suspect, than anybody else has in the introduction part, and just try to introduce how physics or chemistry really leads into engineering. Engineering is just applied chemistry or applied physics. And how applied it is really a function of how mature the field is. So civil engineering, for example, is very, very mature. You'd suspect that that one might be pretty darn applied. And you can't get much more applied than building roads and bridges and buildings. Whereas nuclear is much less mature, and we still depend very much on pure physics to determine a lot of our phenomena. You know, we're not really at the cookbook engineering stage yet. Anyway, what is radiation really? This is very important to understand nuclear power, the hazards of nuclear power, to feel comfortable, because radiation is all around us. You've heard this before, I'm sure. But the universe is awash in radiation. And what we produce is absolutely no different than what is bombarding us all the time. So we'll talk about that. Todd Gonzaghi is going to pick up more on the nuclear energy fundamentals, what nuclear power is, the balance of plant and so forth. One of us is going to expound on, is nuclear waste really such a big deal to worry about? It's a problem, but is it a big deal? We'll see. Health physics and shielding, very important topic. And I would close with just, will fusion save the world in 50 years? It's always been 50 years. But I don't know if we'll have time in this class. But okay, so we did this. What do you think about nuclear power? List 3 disadvantages of nuclear power, or 3 advantages. I won't go into what I think they are, but you know, it's things like high power density, potential of very high thermal efficiencies, virtually unlimited fuel supplies, good central generation capability. I don't know. 3 disadvantages. Well, you do have a waste disposal issue.
You're cutting in and out in B16.
Okay, operator, please. They'll give it a try. If I cut out completely, have somebody walk over and tell us.
You sound good in Idaho Falls, so it's a local issue.
Yeah, thanks, Todd. Okay, 3 disadvantages. Well, there's the potential of an accident, which if the accident occurs, even though it's very, very low probability, the consequences can be rather dramatic. And it also makes a right royal mess to clean up, as they found out in Chernobyl, which really was an uncontained release. Rank the following energy sources. There's good reasons for any one of these, really. And why'd you pick number 1, number 2? Okay. So what kind of engineering topics are there, and where does physics feed into it, or chemistry, if you will? Civil, mechanical, electrical, nuclear, chemical, environmental, computer engineering, computer science, whatever. So, what would you say was the oldest engineering profession? I'm giving the answer away, obviously, right away. But you would have said this anyway, I think, right? Clearly, civil engineering is the oldest engineering profession. It really was born thousands of years ago, 5,000, 6,000 years ago, whenever mankind gave up the nomadic life. You know, nomads don't need structures. They don't really need roads. All they need is a horse, and they wander around. But as soon as people, mankind, started to collect into civilized cities, or cities, I should say, then sanitation becomes a problem, housing becomes a problem, fields becomes something you have to deal with. So roads and bridges, sanitation systems were the first civil engineering. Okay, so where's the physics? Well, everywhere. I mean, balance of forces, fluid flow, and so forth, going to civil engineering. Probably considered the father of civil engineering is Archimedes, and he was around 200 BC, 300 to 200. But really, the Romans really did mature the field. And this is a classic picture. You see it in history books, History of Western Civilization. It's a viaduct in France. Now, I think Dr. Savage, if he did the civil engineering, he probably showed you that beautiful bridge in France, the modern bridge that spans, maybe not. It's just opened about 3 years ago. It's already considered one of the engineering marvels of the world. It is absolutely stunning. But this bridge is just as stunning because it's 2,000 years old. This bridge was built during the reign of Augustus as an aqueduct. This is part of an aqueduct system to the city of Nîmes in Provence in France. The aqueduct system ran some 30 miles. This bridge is called Pont de Gare because it goes over the Gare River. It is still standing after 2,000 years, even through the Dark Ages, even through the barbaric times in Europe. So this is a marvel of engineering, which proves my point that the Romans were really the best civil engineers of all time, including now. That's my humble opinion. Because, and to back that up, this bridge is the only bridge on the Gare River that has not been washed away. Every bridge that they have built in history, except this one across the Gare River, has been washed away by floods, including one 20 years ago that was built 30 years ago. This bridge was so well engineered, and there's subtle little things. There's a bow to it. You can't see that, can you? There's an actual bow to it, so it faces upriver, like a bow of or a bow of a ship. These big arches there are not for beauty. They're to let the water through. So in a flood stage, you know, this would be a pretty high flood. There's a person, right? So you get an idea of the scale. It's a big structure. Now, how did they build that in 20 BC? Lots of people, lots of labor is the only thing I can say. Beautiful site. The last bad flood there was about 5 years ago. I was in France at the time. And they had built a beautiful new visitor center on this bank, the left bank, if you will. Beautiful thing, completely washed away. Not a sign left of it after the flood. This is the third visitor center that's been washed away. They finally gave up. There's a pretty good-sized hill over here. They put it about a half a mile up that hill, away from the river. So your visitor center isn't anywhere near the bridge. But the bridge is fine. All these floods, devastations and stuff, the bridge is fine. Just another picture of the same. Beautiful structure. Another view. Here's another old bridge in France, very close to where I lived. I lived in France for a dozen years or so, if anybody didn't, well, most of you probably don't know. Anyway, this is just a little petite bridge over a small little stream, which is pretty dry right now. There's a little water in it. But this is another stream that really floods badly. And you can see these are actual penetrations, it's for aesthetics, it's also to let water through. So when the flood stages get up to there, there's a path for the water. And so this bridge has withstood many, many floods. Now the neat thing about this one was, up until about 4 years ago, it was still used for traffic, trucks, cars. And so I would drive people, we would kind of go along driving down the French countryside. I'd go over this bridge, which looks like just a road, stop on the other side and say, you just went over a 2,200-year-old bridge built by the Romans. This is like 200 BC, this bridge. It was on the Florian Way. It was the route between Italy and Spain that the Romans had. They closed this bridge to traffic about 4 years ago. They built a new bridge just parallel to it and keeping that as a historic landmark and so forth. And the article in the paper said, you know, the old girl deserves a rest. She's been working for 2,000 years. But I can almost guarantee you that in 100 years from now, that bridge will be standing and the new bridge will be gone. Almost assured. So, anyway, enough of the Romans. They're fascinating. They were by far the best civil engineers. Phenomenal civil engineers for what they had to work with. Anyway, all right, mechanical engineering. Obviously, mechanics come into mechanical engineering. So the father of mechanical engineering, well, depending on if it's mechanics, Newton, 1600s. The thermodynamic side of mechanical engineering would be Joule, you know, the early 1800s. Fluid flow, Bernoulli in the 1700s. So my point is, civil engineering really matured with the Romans 2,000 years ago, even without complicated computer codes. But the field really matured. They built things, and they built them well. Mechanical engineering is a field where we use thermal energy to produce heat or to produce power or do work, probably matured in the 1700s, I'd say. So with Fulton and the steam engine and so forth. Electrical engineering is a little later. See where I'm going? I'm going from oldest to newest. And obviously, nuclear used to be the newest. Now I suppose you'd say bioengineering or nanotechnology would be. That'd be true. But we used to be the youngest. Now we're not. But certainly Maxwell in the late 1800s, Faraday, Tesla, Edison, and so forth. Late 1800s is when I would say electrical engineering matured as a field. Nuclear engineering is considerably more recent than that. Madame Curie was probably the first, well, was the first to really study radioactive materials. Obviously, Einstein was the key. His famous energy mass relation, E equals mc squared, is what makes nuclear power work. Also what makes nuclear weapons work, unfortunately. But this was the very early 1900s, and of course nobody had any proof of his theories that early. They were just theories. But things started to come together just before World War II, and the neutron was discovered in 1932, and a pair of Germans discovered fission in 1939. And then after fission was discovered, the genie's out of the bottle. There's no question. You can't go back. So after that, unfortunately because of the war, there was a huge growth in nuclear engineering or nuclear science knowledge. And it was really carried on by the Manhattan Project, which was the secret project to build a nuclear weapon. Right? And components of that project grew into the first national laboratories in this country, which were first Atomic Energy Commission and then Department of Energy laboratories. So at Chicago, where Enrico Fermi was the project there was called the Metallurgical Laboratory, which was just a code name. They did nothing metallurgical there. They were pure physics people. As some of you know, the first nuclear reactor was in Chicago in 1942. And that is now Argonne National Laboratory. My old alma mater, so I have a little bit of pride there. Tennessee grew into Oak Ridge National Laboratory. Why Tennessee? Well, because of the Tennessee Valley Authority had cheap electricity, and they needed cheap electricity to run these separations plants to produce enriched uranium-235 for weapons-grade material. Same thing with Hanford. The Hanford works in Washington were placed there because of the Columbia River hydroelectric capability. And so there was plenty of cheap electricity in both Tennessee and Washington, hence you had two components of the Manhattan Project there, which then grew into national laboratories. If anybody's from the Hanford area, you know all about PNNL and the Hanford Works and so forth. New Mexico is where they assembled the bomb. The final team of scientists got together from around the country at Los Alamos. It was a very isolated old Indian school, a school for American Indians, Native Americans, about 40 miles from Santa Fe, up on the mesa, really pretty site. And Robert Oppenheimer, the director, the first director of Los Alamos, and the one who basically assembled the team to build it and test it, had gone on vacations when he was a child there. He was a New Yorker, I think. He was an Easterner anyway, from California. But anyway, he knew the area, he chose the site. Now, it's all chance. These things could have been anywhere. You know, if Oppenheimer had gone to school or taken his vacations in the Sawtooth Valley in Idaho, Los Alamos could be in the Sawtooth Valley, which would be a shame. But New York, Brookhaven National Laboratory, big, that's where, through Columbia University, some of the mathematicians worked there during the war. And then in California, we had Berkeley Laboratory and Lawrence Livermore Laboratory. So the first reactors, 1942, CP1, we call it that. It's called Chicago Pile -1. We go up to 20 or so CPs, including EBR1 that's out in the desert. People that have seen the national landmark there. EBR1 is got a CP designation of, I think, CP4 or 6, don't remember. The reactor testing was moved out of Chicago, for some reason, to Idaho in the 1950s, and hence the National Reactor Testing Station was born, and which then has now evolved after 40 years, 50 years, into the Idaho National Laboratory. President Eisenhower signed the Peaceful Use of Atomic Energy in 1955. That declassified a lot of stuff that was classified by the war. At the same time, EBR1, Experimental Breeder Reactor #1, lit the first light bulb, as far as we know, the first electricity generated by atomic power, by nuclear energy, in 1955. And you can go see that site. It's between Arco and Idaho Falls, out on the INL. It's open to the public in the summertime. Self-guided tours, or students give tours. And it's really quite interesting. I mean, that is not the first reactor, but absolutely the first one to produce electricity. It had a full thermodynamic steam cycle. Not a lot of power, I mean, a few hundred watts, but still. And then Borax was the first boiling water reactor. Also was actually built right next to EBR1. Was the first that hooked into the grid and supplied electricity to Arco. Again, circa 56, that same time period. And these both have CP designations. They're both Argonne designs. Okay, why nuclear reactors? Well, in the beginning, all the scientists that worked on it knew the potential for electricity production. But their first purposes were very war, defense-oriented. Offense-oriented, is a better term. First used to produce plutonium for weapons. So that's the Hanford works. Then when thermonuclear devices became, well, the rage, literally, they built reactors in Savannah River to produce tritium. Now, most of you have had enough chemistry in high school or physics. These terms mean something, but you'll learn a little bit more as we go along. The first production reactor, or first reactor to produce power, was in Pittsburgh, Shippingsport. And then for naval propulsion, primarily submarines, but also aircraft carriers. Obviously, the advantage of a submarine, you don't have to come up and charge your batteries by running diesels, with a little snorkel. So you can stay underwater for 6 months. I think the crews run out of sanity before you have to come up for food or anything like that. Can you imagine being in a sub, under the water for 6 months? Can you imagine being under the polar ice cap? Talk about a claustrophobic feeling, knowing that not only in this tin can, you've also got, 1,000 feet of ice above you, so you could never hope to escape. Oof. That's why they do very careful psychological testing of the submarine corps. I would fail. I guarantee you I would fail miserably. Now, of course, we have a lot of use for medical isotopes and for imaging. Every time you get an X-ray, that's an application of nuclear physics or nuclear science. So what is a nuclear engineer? This is important. If you're not a nuclear engineer or you are one, you're not sure what you are, and since you're just starting out in the field, well, you could be a mechanical engineer with a nuclear bent, or a nuclear engineer with a mechanical bent. And in nuclear power plants, there's a huge area of thermal hydraulics because of both designed for efficiency, thermodynamic efficiency, and also for safety. Melting things always seems to be the ultimate problem. All right, you lose coolant in your car, your engine burns up. That's not a good thing. You lose coolant in your reactor, and your reactor burns up. That's an even worse thing. All right, just picture you don't just stop and take it to the junkyard. You've got a problem, so you protect that. That's thermal hydraulics. That's primarily mechanical engineering. You could be an electrical engineer because we have to control nuclear reactors. We have to control them well. safely, reliably. We don't want them to run away. Again, the cruise control in your car runs away. All right, you got a moment of panic. If you're smart, you turn the key off. If you're not, you crash into the car in front of you or whatever, but you usually come out of it okay. Your nuclear reactor runs away from you, you know, then it's a little bit different scale. Exactly the same problem, but the consequences are greater. So you pay more attention to it. You have to pay more attention. You could be a civil engineer, where you've got seismic and structural. You could be a chemical engineer. We've got fuel cycle issues to deal with because we generate all kinds of fission products, and so, you know, got that. You could be a physicist, just a plain old physicist, and decide you wanted to go into nuclear field. Plasma physics, medical physics, reactors, whatever. This is just a little fly. We are a full-service department. We offer all degrees, BS, MS, and PhD. We're actually the only department that offers uniquely all three degrees. There is an engineering and applied science, which is sort of a catch-all for the PhD, but we offer a nuclear science and engineering PhD specifically. Wide range of interests to the faculty, good facilities. We've got a small reactor, which is really a blast, even though they don't let me touch it. You know, good activities up at the Idaho Accelerator Centers. There's just a lot of opportunities. So, oops. Oh, okay, I guess I need the Elmo. Please. I guess that's, perfect. So, that's sort of just an overview of the history. And I don't want to bore you with a lot of stuff here because this is supposed to be fun. But, all right, so now we're going to talk a little bit about what radiation is really and some of the fundamentals. But if we think back before Einstein, before Albert Einstein did his E equals mc squared, which is an equivalency, everybody knows this equation. But it's kind of profound because it says there's an equivalency between energy and matter. And before Einstein, the chemical rule was that matter nor energy could neither be created nor destroyed. So if you had a certain amount of fossil fuel, coal, and you burned that coal, if you measured all the products that came off that burning, all right, the carbon and so forth, you would get no change in mass. That mass, the components of the burning of the coal would be the same as the lump of coal in the first place. So that led to the concept, you can't destroy matter. All right? The process doesn't do it. And same thing with energy. Now, the concept has to say something different. And that's that matter and energy are completely interchangeable. So we talk about matter, mass, in terms of energy. We'll give masses in terms of mega electron volts. You know, an electron is 0.5 kilo electron volts. That's its mass. But we're giving it in units of energy. So now, yeah, the difference is when I burn coal, I get combustion products that are the same mass. When I burn a lump of uranium, I don't get the same mass back. And what the difference is what we call a mass defect, and it's the energy that's left over. So I'm getting ahead of myself. What kinds of energy are there? Potential energy, right? Potential is probably the first one that was ever used by any kind of engineer. Falling water, you know, a dam, Archimedes, screw, those kinds of things. So I think potential energy probably is the one that mankind discovered first. Kinetic energy is what? Well, that's when the water falls. So the potential energy is the water up here. But then when the water falls, that's kinetic energy. And that's when it does work. Potential energy really can't do work. It has to be converted into something else. So what other kind? So kinetic is 1/2 mp squared. Potential is gravity. obviously. What about chemical? Batteries? Right? Electrical potential energy? Sure. Thermal? So thermal energy in this room, I'm feeling pretty warm up here. So I'm feeling a lot of these little molecules are bouncing around at some higher speed than they used to be. Because that's all it is. Temperature is a reflection of the average speed of the molecules in the room or in a material or whatever. So that's a reflection of thermal energy. My point is that there's a lot of different kinds of energy. And they're all things we've studied or will study. Those of you that are mechanical engineers will study this into great detail. We nuclear engineers study that, but we also study this one quite a bit, the equivalency. Oh yeah, I talk about MEVs. What the heck is an MEV? Does anybody know what an MEV is in this room?
An electron volt.
Yeah, well, a million. MEV. And what is an electron volt? Why is that energy? Okay. If I have a potential of 1 volt, 1 electron and it's charged such that the positive is down here. The kinetic energy that 1 electron obtains by passing through a potential drop of 1 volt is 1 electron volt. That's why it's energy. So it's really potential energy until I release it. It's a potential energy that's contained here. If I release it, it gets that much kinetic energy, but that's 1 electron volt. It's 1 electron falling through 1 volt of potential. Now, is that a lot? Is that a little?
It's tiny.
It's tiny. Exactly. Because one MeV then is either 1 electron falling through 1,000,000 volts or 1,000,000 electrons falling through 1 volt. Either way, it's a whole bunch more. It's 1,000,000 times more. That's only equal to 1.6 times 10 to the minus 13th joules. Now, 10 to the minus 13th is a pretty small number. Now, remember, 1 watt is 1 joule per second. Okay, so I've got 10 to the minus 13th, the potential of 10 to the minus 13th watts. That's less than milliwatts. That's less than nanowatts. All right? That's not a whole lot of energy. So, actually, an MEV is I suppose MEV is quite a bit less than a wet mosquito flying into you. But where it comes in, all right, and so we talk about 1 MeV neutrons, 1 MeV this, 1 MeV that. And for us, it's a fairly large number, but obviously in the grand scheme of things, it's going to take a whole bunch of these things, a whole bunch of MEVs to make usable power. So, and you can actually do the conversion, if you wished, to get 1 megawatt, or better yet, 3,000 megawatts to get roughly 1,000 megawatt electrical. Okay, how many MEVs do I need floating around per second? Well, a lot, okay? I've got 3 times 10 to the 9th here and 10 to the minus 13th here. So I just need a whole heck of a lot of MEVs, 10 to the 20th ranges. But there's a whole lot of material in the world, so I have a whole lot of MEVs potential. All right, fission is when we split the atom. Basically, a neutron comes along and hits a nucleus of something like U-235, and this splits into two what we call fission fragments. One of these could be, for instance, barium. This could be krypton. There's some electromagnetic energy coming off with that. And then there's a couple of neutrons. Maybe two, maybe three in that process. And so these guys are where the bulk of the energy is, and that's about 168 MeV. The total process is about 212, something like that. Some of it's unrecoverable, some of it is, but the bulk of the energy we get is in these fission fragments. They slow down in materials, and that creates heat, which we can then use to boil water, generate electricity, whatever. Now, I think Todd's going to cover this in much better detail in terms of the actual energy you get and power and so forth. So, and you're going to get more of this too. I'm just giving you overviews. But what's in the nucleus? Well, first there's the proton. That's a positively charged particle thing, basic, binding or building block. Neutrons. They're neutral, hence the name neutron. Don't do that. No charge. And then electrons, of course, are negatively charged. And so any atom, any nucleus is made up, any atom. Obviously, the nucleus is only the proton and neutron. So we have to balance charges. So a hydrogen atom is going to have one proton and one electron. Poof, that's it. A helium atom is going to have two protons and hence two electrons. And it happens to have a couple neutrons as well. Or maybe three, maybe two, maybe four. We have then isotopes of these things. So I can have deuterium, which is called heavy water. It has still one proton. It has still one electron, but it also has a neutron. So it's twice as heavy as the hydrogen nucleus, right? Because these two are about the same mass, and that's really light. So that's an isotope of hydrogen. The key thing here is that it's exactly the same number of electrons, and those that remember your chemistry, remember that electrons dictate the chemistry of anything. So heavy water has the same chemistry as light water. We go all the way up to U-235, which is important to us, and it has 92 protons and 143 neutrons. And how many electrons? 92. Okay. Todd, I want you to cover mass defect and things like that a little more than I'm going to, okay? Okay?
Happy to.
Thanks. But I want to, and we still have some time, a little bit. The one thing I do want to talk about is somewhat philosophical, and that's the so-called binding energy per nucleon curve. We have this equivalency, and what we find is, for example, a hydrogen atom is made up of one proton and one electron. So I have the mass of the proton plus the mass of the electron. And I've got the mass of the hydrogen atom over here. It turns out, and this is where energy and matter are interchangeable, that the mass of the hydrogen does not equal exactly the mass of the proton plus the mass of the electron. And you say, how can that be? The difference is what we call binding energy. And the binding energy is what holds the thing together, what holds nuclei together, and this is the equivalency that delta M is equal to the binding energy is equal to delta M C squared. Right. And that's what we release when we fission. The mass of our U-235 is not equal to the mass of the fission fragments that come off in the neutrons. And there's extra energy liberated in the form of this binding energy. So, but I just want to introduce that because it is the glue that holds everything together. And this curve is the curve of the universe, if you will. It's got the life and the birth of the universe all contained in it. What this is the number of nucleons in a nucleus. So U-235 would be up here. It's got 235 nucleons. Hydrogen is way down here. It's only got 1. And on this side is the average binding energy per nucleon. So it's what holds it together per nucleon. And you see that light elements come up from here, low, and go up to here, and then it peaks, and then heavy elements come this way. You're going to the most stable element is up here because it's got the most binding energy that's holding it together. So it's the most stable. That peaks at iron. And so iron is the most stable element in the universe, which tells you, due to thermodynamics, entropy, and so forth, that eventually the universe is all going to go to iron. And that's where stars end up. They end up going to iron as the death of them. And so the medieval people always knew that iron was the base element. They considered it very base. And they didn't know why, but it turns out they were completely right. From nuclear physics, iron is the most base element. It's the most stable in the universe. Everything else here is unstable to some degree or another. So what you see on this side is fusion, because you fuse two together and you get up higher, you release energy. You see on this side fission, you split them apart, you go to higher points on the curve. You release energy. So there's a lot contained in that silly little curve. There's some funny ones in here like lithium-7, lithium-6, helium-3, which are typically, I mean, you think of fusion only on this side, but these little blips here give you some fission reactions on this side as well. Helium-3, for example. Okay, types of radiation. You'll get this later in the health physics side, but neutron, beta, alpha, gamma, whatever, I'm not going to talk about. But I'm going to talk about gamma radiation and X radiation just a little bit, because everybody's afraid of them. I know you're afraid of it. Everybody's afraid of gamma radiation. It's scary. Neutrons, you say, oh, heck, they're just a bunch of billiard balls. They're not going to hurt me too much. But gamma and X-ray radiation, we do pay special attention to because it's a penetrating type of radiation. The other radiations are very easily stopped with fairly modest shielding. But gamma and X-ray radiation, because of their energies, are much more penetrating. But I want to tell you just what it is. It's just electromagnetic radiation. And it's governed by its frequency, just like a radio wave, just like your FM dial is so many megahertz on the thing. We have a frequency for it, which is speed of light, 2 pi lambda, that's pi, wavelength in a vacuum. And that is proportional to the energy of the wave. So what is electromagnetic radiation? Well, these lights are electromagnetic radiation, right? I turn them off, it goes away. I have no radiation anymore. That's electromagnetic radiation. What about your television signal? It's electromagnetic radiation. Your radio signal is electromagnetic radiation. What about your microwave? It's electromagnetic radiation. What about, I said lights, visible light, electromagnetic radiation. It turns out that what we have is what we call the electromagnetic spectrum. And all radiation is the same. It's electromagnetic radiation. It's either polarized, non-polarized, transverse, whatever, but it's all just like you had in physics class where you took a string on one side and you went like this and you created waves, right? That's all this is. Its only difference is the wavelength. You can't read that too well, but radio waves are on the kilohertz, 2 megahertz region. So you know that the old AM bands were kilohertz, FM bands are megahertz, TV stations or TV channels are both higher megahertz, and so forth. You go radio waves, microwaves, infrared, visible, ultraviolet, X-ray, gamma ray. And so it's interesting that visible light here in the middle of the spectrum is a higher frequency than microwaves. So that says visible light actually carries more energy than microwaves. And you say, how can that be? I heat my cup of tea or my cup of soup with my microwave. Well, it's just a matter of power. But the fact is that for a given photon, if you will, visible light is indeed more energetic than a microwave. Because this spectrum tells it all. It's all based on wavelength, because the higher or the shorter the wavelength, go back to my this relation, if the wavelength is small, the energy is high, and the frequency is high. So the only difference between visible light, or a microwave, and a gamma ray is the energy, the frequency of it. That's the only difference. It's exactly, precisely the same energy, or the same phenomenon. X-rays are just down a little bit higher. But what that does, I mean, I shouldn't be disingenuous about this, because the only difference between a bullet at rest and coming out of a gun is the energy, right? So a bullet coming out of a gun is quite dangerous, but if I throw it at you, it's not so dangerous. Well, that's the same thing. You know, me throwing the bullet is up here, and shooting it out of a gun is up there. It's only a matter of the energy that it contains. But what I want to get at, and really emphasize, is there's no difference in what it is. You know, it is what it is, which is an electromagnetic wave, period. There's nothing magical or sinister about gamma radiation or X radiation. It's just the fact that their energy is higher. And so if you understand it that way, then you realize you can control energy. You can shield yourself from it. I mean, you don't touch a hot stove or an oven voluntarily, right? Well, that oven is only a matter of energy, temperature. You burn yourself if you touch it. Well, if you play with gamma rays, you'll burn yourself in the same way. But you don't have to play with them. You be careful with them, just like you do with your oven. But again, there's no such thing as man-made radiation. There's radiation that comes out of man-made things, but it's exactly the same radiation. That's the important thing. There's some errors up here in terms of penetrating the Earth's atmosphere. The fact that visible light penetrates the Earth's atmosphere is actually it's a gift from the creators or whatever, because it's just a window in certain absorption cross-sections of molecules in the Earth. But these are wrong. Not all radio frequencies penetrate the Earth's atmosphere, specifically the ionosphere. AM band does not. All right. The AM band essentially reflects off the top of the atmosphere. It won't penetrate, it reflects, which is why if anybody listens to AM anymore, you can get stations from thousands of miles away on AM. It's because it is actually looking at the curvature of the Earth, there's an AM station here, and you're over here, it actually does a reflection off of the ionosphere up here. It doesn't penetrate. FM, being higher frequency, energy again, is more penetrating, and so FM, because of the higher frequency, the ionosphere can't respond, and FM does penetrate the Earth's atmosphere. It's all a matter of frequency and energy. That's all the difference is. Gamma rays, of course, X-rays don't because they're lower energy, but of course gamma rays can penetrate the Earth's atmosphere because we're bombarded by cosmic rays all the time. Right? We're getting cosmic rays as we speak, which are gamma rays. They're just up here. You know, no biggie. We're awash in it. It's everywhere. It's the same radiation. Nuclear power plant does not produce any different kind of radiation. It's precisely the same, measured the same way. It's not colored green and bad for you. It's just the same. So that's a good place to end. Todd, you're picking up next week, right?
Correct, I pick up Monday.
Okay.